Now the structure of DNA and the structure of RNA are critical for the function that DNA and RNA carries out. So if we want to understand DNA function, we need to first understand DNA structure. One of the things you need to know now or remember from Module 3, because we mentioned it only very briefly there, is that there's a directionality to the way that DNA works. And DNA always is read and made and talked about in what's called the 5' to 3' direction. Where do these names come from? Why do we use the terms 5' and 3'? Well, you may or may not know, depending on whether you've taken an organic chemistry class, that when we have carbon-containing compounds, in other words, organic compounds, in a ring structure, that we number the carbons of those rings, 1, 2, 3, 4, and so forth. So these ring structures are numbered. Remember that the bases, adenine, cytosine, guanine, thymine, are ring structures, and so those have numbers. So you've already used the numbers 1 through 5, 1 through 8, however many carbons we have there. We've already used those numbers in numbering the ring structure of the bases. But now we've got another ring. We've got the pentose ribose. It has 5 carbons. We've got to number those 5 carbons in a ring. We can't just number them 1, 2, 3, 4, 5 because we've already used up those numbers on the base. So now we're going to use 1', 2', 3', 4', and 5' as the numbers that we see on this ribose ring that makes up part of the backbone of DNA. So here we are again, 1', 2', 3', 4', and 5', and we're numbering carbons. Remember that each time we see 4 lines converging on a single point, that means that atom is making 4 bonds. In an organic molecule, we assume that that's carbon. So every time we see 4 lines coming together, we know that there's a carbon atom there. 1', 2', 3', 4', 5'. That 5' carbon is written out. Recall that we have a ribose phosphate backbone, and so what bridges these ribose sugars, these pentose sugars, is a phosphate group. So we have a ribose and a phosphate, and a ribose and a phosphate, and a ribose and a phosphate. The phosphate oxygen atom comes in at the 5' carbon, goes out at the 3' carbon. So that's why we call this a 5' to 3' direction. We're talking about where the ring structure is attached to and where the ring structure is attached from. So that 5' to 3' direction, it turns out, is the only way that enzymes in our body work. We can only make DNA, we can only read DNA, we can only use DNA in a 5' to 3' direction. It sounds like we might be giving something away, but this actually gives us additional power, because if you think about a language, just like the language English is read left to right, other languages like Chinese, Hebrew, Arabic may be read right to left. The way in which we read the language defines the language itself. English doesn't make any sense when read right to left. Like in the Steve Goodman song, Talk Backwards. Okay? English doesn't make any sense if we read it from right to left. Arabic doesn't make any sense if we read it from left to right. The order that we put the elements of language in defines the meaning of that language. And in the same way, the order in which we put these elements of DNA, the bases in that particular language of DNA, A, C, G, T, the order in which we put those bases defines what the language is, as we're going to see. When I write DNA or RNA, when I look at it, when I manipulate it, when I use it, I always do those things in a 5' to 3' direction. So in the example that I show you here, this is UGCA from 5' to 3'. It is not and cannot be ACGU. Now looking at that example, UGCA, is that DNA or RNA? Well, we said that DNA has the bases A, C, G, T. RNA has the bases A, C, G, U. So this must be RNA because we see a U in it. So if we see a T as a base, we know that that's a DNA molecule. If we see U as a base, then we know that that's an RNA molecule. So what we're seeing here is an RNA molecule because we're going from U to G to C to A in the schematic diagram, and we're going from the 5' to 3' direction. A DNA molecule is shown on the right-hand side of the slide. We know that because it's a double helix, and we know that because it has the base thymine in it. So let's look at that DNA double helix again in more detail, and this should be familiar to us from what we saw in the previous slide. We have a sugar phosphate backbone. In this case, the sugar is deoxyribose. We're still moving in a 5' to 3' direction. Notice that the sugar phosphate backbone comes in at the 5' carbon, goes out at the 3' carbon, comes in at the 5' carbon of the next deoxyribose, goes out at the 3' carbon of the next deoxyribose, and so on and so forth, moving along in a 5' to 3' direction. The other strand runs in a 5' to 3' direction, but what we call anti-parallel. So if we draw an arrow showing us the 5' to 3' direction, the arrow for one band of the helix is going to move in the opposite direction from the other band of the helix. Think of these as two spiral staircases locked together, and one spiral staircase is only to go up, that's shown in the blue spiral staircase, and one spiral staircase is only to go down, that's the lilac or the lavender or the purple spiral staircase that we also see locked inside of here. And these two spiral staircases are held together by the hydrogen bonding of the pairs A to T and C to G. This is what maintains the structure of the double helix. It was this model that we're showing in this slide that Watson and Crick got the credit for discovering, even though you can say in a very real sense that Rosalind Franklin had the hard physical data to prove the existence of this model. I'll give Watson and Crick credit for thinking of the model, but Rosalind Franklin had the data that proved that the model that they conceived of was the correct structure.